Unit 2 Chemistry, Chapter 20, Part 2, looking at some process called volumetric analysis. So this is using the stoichiometry that we looked at in the last video, and the solution stoichiometry, to find the exact amount of an acid or a base in a substance. And essentially what we're doing is we have our solution with an unknown concentration, but we react it with something that we know a lot about, which we call our standard solution. And then, using the amount of our standard solution, we can find the amount of our unknown solution that we're trying to find out. So our standards are really important here. First thing you've got to do is make a standard. To make the standard, you weigh out very accurately a mass of a substance that you know the molar mass of. Okay? It has to be something which is pure, but it also has to be something that we can access quite easily. Okay? From the mass we can find the amount in mole. We then put that into something called a volumetric flask. The volumetric flask accurately measures the volume. Now, remembering that concentration is amount over volume, once we've got the amount and we've got an accurate volume, we can find the concentration accurately. So the things our primary standards need, they have to, as we say, be ready, available in pure form, and we have to know their formula. They also have to stay on our shelf without breaking down or reacting with the atmosphere, otherwise they're no longer pure. In an ideal world, they're also relatively inexpensive, so we can make lots of it, and also have a high molar mass, because if the molar mass is very low, then a slight change in how much is weighed out will lead to a big change in the amount in mole that we work out. So we might use sodium carbonate if we want a base, or sodium borate, and we'd use a base if our unknown that we're looking at is an acid. If our unknown is an acid, then our primary standard needs to be, if our unknown is an acid, our primary standard needs to be a base. If our unknown is a base, the primary standard needs to be an acid. So for acids, we wouldn't use strong ones, we'd use weak ones, such as oxalic acid or potassium phthalate. Okay, we use some special equipment for volumetric analysis. We've got a volumetric flask that we make our standard solution is. We then got a pipette. The pipette is used to measure a specific volume, normally of the unknown solution. Okay, that specific volume we call our aliquot. So the aliquot is the name for what we put in from the pipette. We use a burette to deliver accurately amounts of the standard normally, but doesn't always have to be the same amount. Okay, from the pipette it's always the same amount. From the burette it can be a range of different amounts. And we have an indicator, a substance that's going to change colour when our reactants are close to being in stoichiometrically equal amounts. Okay, so our indicator is itself going to be a weak acid or base, naturally found, and when they accept or donate protons, they change colour. You don't need to know how that actually works, but just know that they do, and different ones change at different pHs. Okay, we don't use universal indicator because that changes very gradually, and that's actually a mixture of a whole range of different indicators. So what we'd use is just one, where we accurately know its end when it changes, and we're going to know that when this one, for instance, methyl red, changes from red to yellow, that's the point at which we need to stop our titration, or our volumetric analysis. Okay, so the whole process is called volumetric analysis. The actual little bit in which you're reacting with the acid and the base is called the titration. So you get your standard with the known concentration, and normally you place that in the burette. You get your unknown, you draw it up in a pipette and you put it into the conical flask. That's your aliquot, remember. You add your indicator, again, to your conical flask, and give it a swirl. You then drop in liquid from your burette really slowly until your indicator just changes colour. Okay, so if you were using this, it goes from red to yellow. You'd want to stop it when it was orange. Okay, you don't want it to get all the way to bright red or all the way to bright yellow, depending on which way you go. Okay, the point at which the indicator changes colour, that's your end point, because that's when you stop. The point at which they're in stoichiometrically equal amounts is known as the equivalent point. Now, if you, or whoever designed the experiment has designed it well, the endpoint and the equivalence point are very, very close to each other. Okay, and we then can use the volume of your known solution to work out the amount in mole of your known, and therefore the amount in mole of your unknown. Okay, so this is our conical flask in which we've put our aliquot and our indicator. This is our burette, and that's where we're going to drip, drip, drip solution from here until this changes colour. We also always put a white tile or a white piece of paper underneath because that makes it easier to see. Now, one thing you will notice is that it's a backward scale. So as we go up here, instead of the numbers getting bigger, the numbers get smaller. What that means is that as we're reading off the burette, we need to look at it very carefully, okay? Because it doesn't matter that it's a backward scale, because all we're looking at is how much got added, okay? But if we look at this scale here, we can see this is our meniscus, and our meniscus is somewhere between 1 and 2, okay? Here is 1.5, yeah? Here, therefore, is 1.4. And the bottom of that meniscus is just about on 1.4, but it's just a little bit below, okay? So we would say that this is about 1.39. We always, always, always record our results from our burette to 2 decimal points, no exceptions. And the last decimal point can't always be 0. So we do that once, and we look at what the initial reading on our burette was and the final reading, find the difference, and that's called our titer. And we've done that once, great. We're going to do it again, and we're going to see if we get the same result. What we're looking for is our titers being within 0.1 of their average, okay? And we want 3 of them that are concordant. So we keep going until we get that. If we get ones that aren't concordant, we still record them on our results table, but then we don't use them in our calculations.